Hello, everyone. We are going to let people trickle in for the moment as we're getting started with our webinar for today. But while we let some people join in, I just wanted to introduce our webinar for the day and also myself. My name is Anne. If you have done any training within the last couple of years, you've definitely been working with me. And for today, we are going to be kicking off our 2026 webinar series by talking about the relations between high frequency heart rate variability, photoplethysmograph, and pulse transit time. So that being said, we are going to start with a couple of announcements as we let people trickle in. So number one, for the duration of this webinar, we will have you both muted and with your audio and video off. If at any time you experience any technical issues, please feel free to send any questions you have into the chat. We have technical support on standby, and they will be able to help troubleshoot any issues that you have. But other than troubleshooting issues, if you have any questions during the webinar, as we start to get into the different topics, please feel free to send in your questions as well. That being said, with the chat, someone will be reaching out to you when answering your questions. And at the end of our webinar today, we will be going through and doing a 30-minute live Q&A. So for whatever questions you ask, we will also be going over them as a group. So in addition to the education initiatives that we're doing with our webinar series, I also wanted to highlight some of our other services that we offer here. So one of my favorite services that you may not know that we do is laboratory design. And for any of you that may be moving positions and designing a totally new lab space, this allows us to come in and really customize your lab by working with your facilities department to give you all the bells and whistles of everything that you imagined. The best part about this is that when working with our laboratory design team, we'll ensure that when working with these multimodal approaches, all of your equipment, all of your data is completely synchronized so that when working with these multimodal approaches on the back end, it makes your analysis much more seamless. So in addition to the big laboratory designs that we work with, I wanted to break this down in kind of a more practical application of how you could use this within your data. So say, for example, you wanted to collect physiology, you wanted to collect audio video through Video Sync Pro, while also getting Tobii Pro glasses for eye tracking and later looking at behavioral codes. We can do all of this and synchronize all of these data streams at one time so that everything is synchronous down to the millisecond. And with this, we would then take all of these data streams and separate them out into their own analyses pipelines. So after collecting all of these data runs, we could go into Mangold's Interact software to do our behavioral coding schemas. We could also go into Tobii eye tracking and relay parts of interest when our participants are looking at stimuli that we've introduced. And lastly, to make it completely integrated, after going through these different analyses pipelines, we could take these different behavioral codes and these different eye tracking codes and bring them and pull them back into our analysis softwares as event markers so that we're really able to use these as behaviorally driven segmentations relevant to your analyses of interest. And speaking of new integrations, one hardware integration that will make talking amongst multimodal systems even easier is our new integration with Cedrus and the CPOD. So for any of you that are using the MindWare mobile, this could be a really great solution for you, especially if you wanted to introduce stimulus presentation that required more millisecond precision. So with this, since your mobile is completely wireless, we would instead use a C-pod to string along a USB connection from your stimulus computer. You could be running SuperLab, Cedrus's stimulus presentation, or any other of your choice. And what this would do is it would send the event markers over to your C-pod, where on the C-pod it would do live event marking and timestamp when received on the device in order to then send that event marker to the acquisition computer. So if you're ever interested in getting more millisecond precision when working with a wireless device, this could be a great solution for you. And feel free to contact our sales team if that interests you. And in addition to some of our hardware solutions, we also have some new software solutions coming up in the pipeline. So when you are working with our programs, if you ever have any ideas for feature requests or custom code that you would like to see done, but you don't know how to do yourself, chat with us. This is something that you may not know, but that we can also do. And the study compiler, which will be coming soon, is exactly my efforts of doing that with our software team. As a researcher, I often was working with long data sets where I was working with ID by variable. However, with our output files as is, we currently get one Excel output file for each individual participant that later on, when working in your analysis program of interest, you're going to need to merge all of these files together to then get them into your larger data set. So this study compiler is a great way of being able to do all of that merging for you and also provide some naming to your segmentations as well. You would be able to come in here and define different areas of interest, so the start and ends of your epics, removing and adding participants to put all pieces of data in, and then eventually defining some of these periods like your baseline start and end to give your segmentations more meaning versus just the typical segment count. This would then, when completed, output you a CSV file in which you could then upload into your analysis program of interest. So again, coming soon, if this is something you're interested in, you could use it on all current data sets, but also all prior data sets that you've used MindWare analyses on. And most importantly of all, I just wanted to highlight that this year, 2026, is MindWare's 25th year anniversary. This is such a big milestone for us, and we are so grateful and thank you to have you with us along this journey. The only reason that we've made it here is because of you entrusting us with your research. So thank you to those of you that were with us in the very beginning and all the way to some of our new customers just getting into physio. We're excited for all the years that this has to come, but most importantly, within this 25-year anniversary year, we are going to be releasing some new lines of technology, both for hardware and for software that meet some of the demands that we've heard over the years as far as what you're looking for in next lines of tech. So stay tuned. We will be having lots of announcements of that in the year as we get closer to that launch date. So now that we've had time for people to trickle in and we've gotten through some of those announcements and reminders, I'm going to transition us into the actual content of today for the webinar. So since we are going to be talking about ECG, PPG, and pulse transit time, we are first going to start with a refresher on ECG, since this really will be the timing anchor that we will ground our PPG and pulse transit time analyses with. So when you think about MindWare, you may think about ECG because this is the most commonly reported metric of all of our measures amongst our customers. And the reason for that is because ECG is considered the gold standard of measuring electrical activity of the heart. And for our purposes today, we are namely going to be paying attention to the QRS complex, namely the R, which provides a really great fiduciary point in order to look at the millisecond differences between beat to beat intervals. And most commonly, when looking at ECG, the metric that is getting reported most is respiratory sinus arrhythmia, where we're able to see that via the vagal nerve activity with the SA nodes on the heart, how we're able to speed up and slow down our heart rate as a product of respiration. So when thinking about ECG in relation to PPG, we need to really think about and ground ourselves in the physiology for what's everything that comes after electrical activation of the heart. So when we first receive from the central nervous system the electrical commands to tell the heart to beat, we are able to isolate this pure parasympathetic marker of vagal activity, in that high frequency heart variability range. However, as it relates to PPG, we need to think about all of the physiological processes that come after this electrical start command. So following electrical activation, the heart then triggers ventricular contraction, where we're pushing the blood out of the heart. And this will then create a pulsate waveform that will travel through the arterial system. With that, the pulse wave will arrive at the periphery sites, but as we make our path from the heart to these peripheries, we're no longer able to isolate this parasympathetic activity. Instead, we now are seeing that we have an influence of both. We will have sympathetic activity at play just due to the signal chain of pre-ejection period and contracting blood out of the heart, as well as then blood pressure introducing more sympathetic activity. So that being said, when thinking about photoplethysmography, we need to really ground it in why this is being used so often. And in the world of modern day wearables, whether you're aware of it or not, you likely have been interacting with this technology. And PPG is gaining so much traction because it's this non-invasive optical method of measuring blood volume changes that is very easy to collect in clinical settings at either the finger or ear, and in the case of wearables, often on the wrist. And with PPG, what we essentially do is we use a light emitting diode in order to see how light absorption in the tissue detects volume changes at these peripheries. And so when the signal arrives at the periphery, this is then indicative of that arterial pulse wave. Let's break it down a little bit further so you can understand more about the technology as far as how we're able to get this arterial pulse wave. Because with PPG, and especially with wearables, you're most often used to seeing this as a metric to derive things like heart rate or heart rate variability. But when we're looking at the technology, we need to really ground ourselves in that this is blood volume changes that we can detect via a light emitting diode. And that light emitting diode essentially shines light onto the tissue, and the blood that is closest will absorb and scatter the light differently than the surrounding tissue. So we're really able to see that pulsate waveform arrive. Versus for some of the more dense tissue like bone, we won't be able to make any headway with that light emitting diode. So as we shine the light onto the finger, we then have this reflected finger, ear, or wrist. We then have this reflected reflected to the photodetector. And this then measures the reflected or transmitted light. So changes in the light then correspond to changes in the blood volume at the periphery. So let's break this waveform down in a little bit more detail so we can see really what we're looking for. So again, PPG is reflective of this pulsate blood flow at the peripheral arteries. And for each pulse that we see, this is going to correspond to one cardiac cycle. So again, everything follows ECG. We get the electrical command for the heart to beat, and then this is then the pulse arriving at that periphery. And with the PPG waveform, this is really broken down into two different phases of activity. The first is the systolic phase, and this is marked by this rapid upstroke that we will see as the arterial pulse wave makes its way to the measurement site. And the point of most interest to us for today, especially when talking about pulse transit time measurements, is going to be the systolic peak. With the systolic peak, this is where we see the maximum arterial expansion. And most similarly, you can think of this synonymous with your R peak as the point that we will be most interested in scoring. And then following this systolic peak, we have this decline in our signal amplitude. And as we hit this decline, we are now entering the diastolic phase. In the diastolic phase, we may also be able to see a dichrotic notch, which you can see here kind of as this leveling out on the way down of this waveform. And this small inflection point is actually indicative of where the arterial pressure is changing following the closure of the aortic valve. So within one full cycle, we're able to get the timing of when the peak is here, able to derive things like heart rate from these peak-to-peak differences. And there's also many other analyses that you can explore related to the width or peaks of widths or peaks of this waveform. But for our purposes today, we're going to be focusing mostly on this systolic peak. So, since we've been drawing so many conclusions as far as how PPG is similar to ECG, one other way that we can use this waveform is, again, looking at the pulse-to-pulse intervals in order to represent the timing differences between these systolic peaks. And again, just like with ECG and the R to R intervals, this is representing one complete cardiac cycle. So with this, we're really able to see with a measure that's very easily collectible, the influence that we can see on respiratory cycles here, as well as like we can in ECG, but there is definitely some more caveats in mind. Since we are collecting at the periphery site, PPG is going to often be much more sensitive to motion artifacts. And we similarly also need to make sure that our sensor placement is snug but not too tight in order to make sure we get good definition around our systolic peaks and to see the entirety of the waveform. And additionally, PPG is also very sensitive to temperature changes as well. So if our participant is cold, their fingers or ears are cold, we'll also see that in terms of the ability for the blood to scatter at those peripheries. So when looking at these two waveforms, we talked about their similarities, but really when they can be best used, in my opinion, is in tandem with one another. And when we're able to overlay our ECG and PPG waveforms, we're able to look at the precise timing of where electrical activation occurred, that very good, clear R peak to assess and use as our grounding point to look at the timing difference, either from the foot of the pulse wave, the midpoint of the pulse wave, or the peak of the pulse wave. And with this timing difference, we're really able to speak to different cardiovascular metrics of interest. So most notably, when overlaying these two signals, people are often looking at pulse transit time. Impulse transit time is the time required for the arterial pulse wave to travel from two arterial measurement sites. So in our case for today, we'll be talking about ECG, that electrical command at the heart, and then how long it takes to travel down this path to the periphery site. So again, ECG will be our anchor just because of that very precise R. And we will then take the millisecond difference between our point of interest for the PPG waveform in order to determine the millisecond delay. When looking at your PPG waveform and determining which point to use, this is honestly up to you and based on your analyses of interest. Most importantly, when looking at any papers for comparison, in order to replicate and extend, just make sure that you're also selecting that same point that they were using as well. Okay, so now that we've talked a little bit about how PTT is calculated, let's talk about why it's so interesting. So PTT really reflects the properties of the arterial system and how efficiently the pulse wave is able to travel through the vasculature. So let's break this down into the general trends of the relationships. If we have a faster pulse wave, what we will see is that we have a shorter pulse transit time and that this waveform peak would be much closer together. Or in the opposite sense of this inverse relationship, we may have a slower pulse wave, and this could be slightly further apart, extending our pulse transit time. Because of this relationship, PTT has been used as an indicator of arterial stiffness and vascular control, namely. And with this, when our arteries are stiffer or when they have reduced in diameter over time, what we're able to see is that our PTT likely is going to be much shorter in general. When we have stiffer arteries, we're less able to dampen that contractility of the blood leaving the heart and arriving at the pulsate waveform. So that being said, with this arterial stiffness, you'll often see these shorter PTTs. And this has also been associated with things like anxious apprehension, anxious arousal, and emotion dysregulation. We're seeing these shorter PTTs. And then opposite, if we have better vascular control, we'll be able to dampen this pulsate waveform and slow the time in which the pulsate arrives at the periphery. When measuring PTT, we also need to take into account different influences that will, different influences to take into account with interpretation. So when we are calculating PTT between ECG and the PPG waveform, since this is a millisecond timing precise measurement, one of the most important features we need to pay attention to is making sure that we have sufficient sampling rates and precise signal synchronization amongst our ECG and PPG. For example, if we had a low sampling rate on our PPG device, we may not be able to get that definition around the systolic peak and therefore not making PTT analysis quite viable for us. So something to consider when thinking about the device that you're using. Other things to take into account here with PTT is the influences that are at hand. So again, since we have sympathetic influence on our signal chain at the pulsate waveform, although we see that high frequency heart rate variability and high frequency pulse rate variability are often very highly correlated, they will start to diverge from one another in as we're introducing our stressors. And that's again because of this sympathetic activation in the signal chain. So in addition to this, we'll also want to take into account things like postural shifts where if we were to observe these in our experiment, we would see the largest differences in PTT at this time. And lastly, when thinking about control factors and what to ask your participant at the time of your experiment, we're going to want to take into account things like age, smoking status, and overall health burden scores as well. So again, thinking about arterial stiffness, as we get older, our arteries will stiffen over time. And same goes for our overall health score and smoking status, depending on the participant's individual variability. This can also negatively affect our PTT as well. So we've talked about ECG as a refresher, PPG as being able to be used given its non-invasive techniques and how to use them together. But we also need to talk about and really kind of drill down based on grounding it in the physiology. What's the difference between these two measures, and when should not be using them based on my research questions? So again, we can derive high frequency heart rate variability from ECG. And with this, we're able to see the variations in respiration and isolate this as a pure parasympathetic marker of vagal nerve activity. So with this and high frequency heart rate variability, we're able to report on RSA with quite accuracy, given that good fiduciary point, and again, higher temporal resolution of the ECG waveform. So conversely, although with the PPG waveform, we can also derive high frequency pulse rate variability. Oftentimes, you will see that people will refer to PPG as heart rate variability, but these two are not the same. They're not interchangeable. But we can still get estimations of how respiration influences this pulse rate waveform. So with our high frequency pulse rate variability, we're really able to we're again able to look at these pulse to pulse differences in order to speak to our regulatory capabilities with that high frequency pulse rate variability. But again, the thing to keep in mind here is that there is sympathetic influence on this signal chain. So when considering if you should use ECG or PPG, it really will be grounded in your research question. Do I need to isolate pure parasympathetic activity? If yes, go with your gold standard of ECG, where we're really able to look at RSA completely reliably and validly. Versus with our high frequency or pulse rate variability, again, able to make an estimation of this, very highly correlated with high frequency heart rate variability, but still sympathetic influence at play. So let's compare the two, getting down into the physiology and then also some of the advantages and disadvantages. So with ECG, we are going to be looking at the electrical activation of the heart. And with this, we are deriving heart rate variability from the R to R intervals. Versus with PPG, we're not looking at the electrical activation of the heart, but instead, again, the peripheral blood volume changes. So here we're able to get this estimation of high frequency heart rate variability, aka really pulse rate variability, via the pulse to pulse intervals. When thinking about the difference in the specs of the devices and often related to the timing of those peaks of interest. With ECG and a lead 2 configuration, you're going to get very high temporal resolution, really defined R peaks, as well as, again, that nice fiduciary point in order to get precise millisecond differences between R to R intervals. But then with our PPG devices, oftentimes with these, we'll see that we're going to have a lower temporal resolution, likely a lower sampling rate of the device. And this can make peak detection more challenging because without having that well-defined systolic peak, this brings into question how usable is our data and what kind of considerations do we need to make in editing. So that being said, when thinking about the advantages of each, it really, there's advantages and disadvantages to both measures. It really just depends on your research question and different factors at play in order to determine what is the best fit for you. So when using ECG, this is again going to give us the most precision, the gold standard of high frequency heart rate variability, and that very clear cardiac timing information. However, with PPG, this is very less invasive. We're only placing a sensor on a periphery site versus 3 electrodes on the torso. It also has a much lower cost of entry, making commercial wearables so readily available to integrate into research. And given this, it also makes it easier to collect in different settings and across larger groups of participants at one time as well. So, when thinking about the two different measures and thinking which one do I choose, there really is no right or wrong answer. We just need to weigh a certain number of variables in order to best make this decision. So, number one, let's think about things like um, where and who you are taking your research and your data collection from. So if we are going to be working with ecological research, we are sending people home with devices in order to get physiology in their day-to-day. It may be much more likely that a PPG device is going to give you the best form factor and the easiest use in order to collect more continuous data or data from multiple participants within the same setting. And with this, we are able to get metrics reliably like heart rate and pulse rate variability, but depending on the actual PPG device itself, we need to take into some consideration of what you're able to access across these various devices in order to know if it's a good solution for you. So, grounded in your research question, whatever your analyses may be, we need to consider how that translates to the physiology and our points of interest. So oftentimes, especially with commercial wearables, we need to be really aware of the specs of the devices. So we need to be aware of the sampling rate, but most importantly, given the commercial nature of the devices, there are proprietary algorithms that are placed on the data that are doing the cleaning for you. You may not have access to your raw data. And because of that, depending on your research question, this may not fly. We may want to make sure that we have absolute total control of our raw data in order to get the most precise timing differences. And again, same thing comes to sampling rate as well. So on these commercial PPG devices, they may be sampling at considerably lower sampling rates than what you're used to with our mobile and Bionex solutions. And because of that, we will only have so many points or samples of where we're able to see that waveform. And if we're interested in things like pulse rate variability, where we do care a lot about the timing differences between systolic peaks, or talking about pulse transit time, where we're able to look at the differences between ECG and the peak of our systolic peak, we need to make sure that we're really able to get precise timing to make sure that those calculations are accurate and valid. And then most important of all, if we're working with just ecological data and wanting longer measures of continuous collection for things like heart rate, commercial devices are great, but if you want to look at multiple measures at the same time, it may not be the best solution for you. So again, when weighing all of these factors, the most important thing is ground it within your research question and also consider things like your budget and your participants and your setting of collection. There really is no right or wrong answer. It's just a matter of thinking of all of these factors at play and what will best answer your research question. So now that we've chatted a little bit about ECG as a refresher, PPG, and using the two overlaid for pulse transit time, we're going to start transitioning into the live demo section of this webinar. So at first, we're going to start by talking about cleaning common PPG artifacts and then moving into calculating pulse transit time. So related to what we talked about before, when it comes to the temporal resolution, we need to think of the common artifacts that we will see and how to best correct them based on the movement artifacts and different influences we see in this PPG data. So number one, we will be looking at this PPG data in our HRV analysis application if we were just scoring just PPG data alone. And most commonly here, what you're going to have to see, or the most common edits that you'll be doing, is going to be point insertions over peaks that were missed and point deletions over sections of tiny pieces of movement that maybe got a point misappropriately flagged versus a true peak. So given this, and given that there's less precise timing of these peaks, we will be doing a bit more point inserting and point deleting than typical. And similarly, when thinking about PPG editing with the point inserts and deletions, the editing rules that we will follow are very closely going to mirror those to what we do for HRV editing. So if you're already familiar with editing ECG in our HRV analysis app, this is going to mirror the same process and the same rules, but just with this different waveform. So similarly, outside of inserting misbeats or correcting for points that are not on systolic peaks, we will also need to mid-beat through sections of ectopic physiology or through sections of movement. And again, just like our HRV analyses, if we are wanting to look at high frequency heart rate variability or high frequency pulse rate variability, we need to be able to get continuous data in order to make sure that we have at least 30 seconds of data to accurately derive those RSA values. So that being said, in sections of movement, in order to correct for this, we will be inserting a mid-beat or an estimated beat as a placeholder over these misbeats or sections of movement. And lastly, the other thing that we'll take into account here today really comes down to the differences that you can see in the data when talking about ECG, which is much more precise and has really great accurate timing, to some of the common issues that we'll see in PPG. So that being said, sensor placement is going to be very important, and movement is also going to play a big factor. When we have sections of movement, we may see that our peaks are going to get slightly distorted as far as not getting the same precision as typical. And most importantly, with sensor placement, temperature changes, we may see that if we don't have our sensors on snugly enough or making accurate contact with the skin and the tissue, we will lose definition around our systolic peak. So we'll talk about this in terms of salvageability of data, of if the majority of our data looks like this. Do we retain this participant over time? Do we not use this participant? And really kind of weighing based on the waveform. And again, to just reiterate this, when it comes to the artifact correction that we'll be doing with PPG, this really will mirror the rules of HRV editing. So again, we are going to want to make sure that we have at least 30 seconds of continuous PPG data. And the reason for this is because we want to make sure that we have enough respiratory cycles in order to validate our fast Fourier transformation and look at that high frequency pulse rate variability. 30 seconds is our minimum, but oftentimes we recommend editing in 60-second segments just so that we can go through and have some flexibility within our data. If we have sections of movement, we can take time off of the beginning or ends of the sections of data as long as we have at least 30 seconds of continuous data within that segment. And again, we don't want to insert too much experimenter bias. And so when we are going through and correcting for data, we are also going to follow the 10% rule of our mid beats, meaning that for every time we place an estimated beat, we are not going to exceed more than 10% of estimated beats across the overall segments. And additionally, we will also limit the amount of mid-beats that we introduce to 3 mid-beats within a row because we do not want to assume more than 1 respiratory cycle. And lastly, when it comes to data retention, considering that movement will likely be more at play here and we may have periods of dropout within our PPG signal when not making good contact, we need to make sure that within a given segment, we can retain at least 50 to 60% of the PPG data in order to use that segment, and also retain 60% of the overall segments within an epic to use that epic to score this participant. So that being said, I'm going to pop out of our program for just a second and transition into the live editing of PPG. So we are going to do a couple of things today. We are going to start by editing some PPG data in the HRV analysis program. This would be standard of if you were only collecting PPG alone, how you would go about scoring it. So for this particular file, I'm working with data collected from an ear PLE, and I am going to analyze this within time mode, again, leaving the majority of our settings consistent with what we would for HRV based on our population of interest for high frequency bands. When I go to hit analyze here and load in my PPG waveform, what you will see is that this is going to mirror much of the same processes of our HRV editing, where our algorithms will come in and essentially do some point detections for us, indicating that blue dots are indicative of good beats and yellow dots are indicative of artifacts that need to be examined just a bit further. So with this, when looking at our PPG data, same rules apply that we are going to same rules apply that we typically do for HRV editing. We will address any artifacts as needed using point inserts or mid beats in order to make these corrections. So this first segment looks pretty good. We've got very well-defined systolic intervals, nice point precision, and all of our peaks are identified here. So I'm going to take a scroll through the data and see what other types of artifacts that we will notice within this given waveform and how to correct them as we are introduced to them. But most notably, with a sea of blue dots of all good systolic peaks, we also would want to verify that our respiration rate and our respiratory time series look good and within the typical range of our population, and also have this respiratory power spectrum peak fall within our white and yellow bands for that high frequency pulse rate variability. So this is ideal. If we're doing our jobs best, we're getting good data acquisition, we will see that we have clear defined peaks that don't require much editing. But as we advance forward and we can start to see some amplitude changes within the waveform itself, we may find that our peak detection is not as accurate as it once was. This is also for a PPG waveform versus the precision of an R peak. So like I said, most frequently when we go into our edit R's to begin editing for PPG data, much of what we'll be doing is going to be related to inserting these points that were missed. So I'm going to zoom in on my x-axis and click and drop about a 10-second window. And with that, I'm able to get more information and more details about the waveform. And this looks pretty great to me. We've got, again, this pulsate waveform arrival, systolic peak, and a fall off. And at this ear PLE site, like I mentioned previously, depending on your specs of your device and your where you're measuring PPG from, you may not have the most definition around your diacritic notch, but that's okay, at least for our purposes today of scoring PPG for pulse rate variability and pulse transit time. So when going through and looking at these waveforms, like I said, from a visual inspection, things look pretty good, just necessarily that the beats were missed. So as I come in here, I'm going to click this insert button, which will create a hover. And I am just going to hover this over the systolic peak and hit insert in order to come in and correct for some of these beats that were missed. So very simple, especially when working with a clean waveform, when you're seeing amplitude changes, this is something that you may need to account for by coming in and just point inserting beats that were missed. But as you do so, you can start to see that we have blue dots when stringing along the continuity of this data. So pretty straightforward, but I would just continue going on, giving a visual inspection to every single beat and making sure that these look good. So I'm going to close out of this. I could continue to keep inserting points for this segment, but I think you understand the flavor of the point inserts. So let's talk about some differences in some different sections of data. For example, when movement is introduced, since this is one of the most common artifacts of PPG data. So since we're at the periphery and at potentially the fingers, one of the most bendiest parts on the body, we are going to maybe get some beats that are some pulses that are inappropriately flagged by the algorithm on some of these sections of movement. So same thing here. I'm going to highlight my little magnifying tool and click the zoom in on my x-axis. And I'm going to cheat a little bit and move over to the section of data that has more movement and just click and drop to zoom in further. And what we can see here is that generally, right before this, we had really good identifiable waveforms, really clean pulses. But as we start to move forward, we're seeing that we're starting to get more pieces of movement and some kind of jagged edges along our waveform. So in the opposite sense here, some of these little jagged pieces have been inappropriately flagged as a peak. So in the opposite sense here, to clean this up a bit, we're going to come through and use our delete key and take away all of these small points that are just kind of lingering around the beginning of the pulsate waveforms, and instead come in and insert beats to correct and fill in the timing here so that we have more blue dots and better continuity, better identification of these systolic peaks. So when closing out, this will correct and give us a much better section of that waveform through movement. And again, these are probably the two most common types of edits you will do in HRV for a PPG waveform. One other thing that I wanted to highlight here is in segment 6, where we have more severe sections of movement. Here, we are looking at data that looks really, really small. And the only reason for this is because we are actually auto-scaling our y-axis in order to accommodate this very large piece of movement. So other than that, we have a lot of blue dots on our pulses, some movement and maybe some things to resolve in the middle. But generally, it did a good job of identifying these pulsate systolic peaks. However, we do have these two yellow beats in this large gap of time that we're going to investigate this a bit further to induce our mid beats. So again, zooming into this section of interest, what we see here is that we have a peak here that we get the systolic peak. we also have a peak on the other side, but in between these 2 points and with this big section of movement, it looks like a piece of data was missed or that a pulse was missed in this section of movement. So instead, what we are going to do here, similar to what we do with HRV, is that continuity matters. We need to make sure we string along at least 30 seconds of continuous data. And because of that, with this gap in time, we need to correct for it or add a mid-beat or estimated beat in order to use a placeholder here. So I'm going to grab my blue X cursors, and I'm actually going to zoom in a bit on my Y-axis as well to give me some more visibility. I'm cutting off the top of this only because I know that this is a section of movement, and I don't care too much about what's going on up there now that I've looked at it in more detail. But what I can see is that, again, I have this gap or spacing of time, and I have a defined systolic peak here. Movement definitely does start to affect this waveform, but still our systolic peak is well defined, that this is a cycle, although affected by movement, is still usable. And we are going to take these two anchors of our pulsate waveform that look good, and we're going to take our blue X cursors and put them on the outside of the pulsate waveform that has that checks all of our boxes, looks good, and drop this X cursor anywhere between the beat that follows it and just after the beat that we like. We're then using this as an anchoring point, and we're going to take our other X cursor and again create this sandwich effect where we are now putting the blue X cursor on the opposite side of the other good beat. So based on this participant's pulse to pulse interval, when we use these blue X cursors to define our anchoring points and the time difference between the two, we're able to have the program determine how many beats should have been within this section of data that were missed. So given this and given this movement where we don't have as good of a systolic peak to accurately score, I would instead place a mid beat here, which will be placed at that 0 amplitude line with kind of this blue circle and a star icon around it, representing this estimated beat. So although we lost the pulsate waveform there, or we weren't confident in where the true systolic peak is, we're able to again correct this waveform and get both of our dots to turn blue, indicating that we've made a correct edit. So again, with these mid beats that we are inserting over sections of movement, we want to make sure that we do not exceed over 10% of estimated beats. And given that, depending on how noisy the section of data is, will determine how usable it is. So within this waveform, granted this is movement for us to come through and edit here, but looks kind of more similar to what we edited a few segments ago, correcting some pulsate waveforms and deleting and inserting points. We will just make sure that we stay under this 10% for the entire 60-second segment. So one other thing that I wanted to talk about here is also the most common artifact when it comes to PPG, which is going to be data loss, likely. So when we, similar to EDA, if you work with skin conductance with our devices, if we start to lose contact with our electrodes or with our PPG monitor, we will lose waveform. And it's a matter of if we have that light emitting diode shining onto the skin or not as the ability to see this waveform. So as I transition from segment 6 to segment 7, things look very different here. We can see this giant section of data. Nothing has been flagged for us as far as any beats, but my suspicion here is that this is probably where we're getting some actual data loss, where the ear PLE has lost contact with the ear. So when I go into my edit Rs and I zoom in, I know this doesn't look like a whole lot, given that we are auto scaling to this big section of movement, but way, way, way under there, I can see these teeny, tiny little blips of what look like pulsate waveforms. So in order to examine this further, I'm going to zoom in heavily on my y-axis, and this time highlighting just the section around this piece of data. So even though we had this big section of movement, and respiration is getting pretty wonky as I zoom in on my y-axis, what we can see here is that there actually was really good data underneath this all that just got missed, given that drop off in signal. As we start to move forward with this data, we definitely see some effects of movement as well that could be corrected for. But ultimately, we have cycles until we completely fall off and lose the data. So that being said, when thinking about how to score for sections like this, we may have signal drop off. We want to consider how much time do we have of good data. So we need at least 30 seconds of continuous data in order to calculate some of those, in order to calculate RSA and that high frequency pulse rate variability. And when working in this 60-second segment, technically, we could cut off data at this 390 mark and take from either the left or right-hand side because it would give us at least 30 seconds of continuous data. However, for what we can see in the data, we do see those pulsate waveforms, but the drop-off occurs just slightly before this 30-second mark. So we could come in and add these pulsate waveforms in, but again, without reaching that 30-second minimum threshold, we wouldn't ultimately end up writing out this segment. So most commonly, these are going to be the artifacts that we see with PPG, but I also wanted to talk about one last example related to PPG that does not have as good a definition. So when looking this time at a finger PLE file, we can see that we do still have some sections of movement, but some good data that's been identified. However, with this finger and at the periphery, we're going to see more movement involved with the actual file, within the actual waveform itself. So given this and given the finger PLE, we do see, again, bigger sections of movement with some pulsate waveform. So I'm going to zoom in here and kind of talk about that other example of what do we do in sections where I have good data, but then I have sections of movement that follow it. And also generally in my good sections of data, do I have well-defined peaks? So in comparison to the ear PLE data that we just saw, let me zoom in a bit further on my y-axis as well. When we zoom in further here, we do have definition in our systolic peaks in certain intervals, but in others, things become a bit trickier. This could be due to sensor placement, sensors not being snug enough or falling off. And so because of that, we also will need to consider how usable is this data. So in this section that we're looking at here, we do have definition around our systolic peaks with maybe some that are a bit more questionable in terms of the accuracy. And this is really where we will start playing a numbers game and based on what we can see within the file as well. So for example, we do have enough systolic peaks here that are well defined in order to retain this data, but it may be that you have data that is so shaky that we are misidentifying these systolic peaks or don't have a clear indicator of our systolic peaks. or just that due to lack of definition, we don't get that we don't get the accuracy of the timing. So it may be that you have some very good sections of data, like segment 1, where we had really well-defined peaks. We would have no problem writing out this data due to definition around that systolic peak. But ultimately, in some of these messier sections where we have less definition, if the majority of our waveform looked like this, or different sections of the participant's recording looked like this would bring into question how usable is this data. So generally, if we have enough good segments and good cycles that have definition, we can definitely still use these participants with point inserts and midbeats around movements of points that lack definition for us. However, if we find that this is characteristic of the majority of the file or the majority of this participant, it may be someone that we don't include in final analysis of that segment, epic, or final analysis of that participant inclusion. Okay, so now that we've talked through PPG editing within the HRV app, I am going to ever so quickly talk about scoring PTT data within our BSA app. So within our BSA app, Basic Signal Analysis, we are able to go into our channel settings and look at our ECG and finger PLE overlaid. And the most important thing when calculating pulse transit time here is going to be enabling calculate PTT from ECG. So on this finger PLE channel, I basically am saying use ECG as my timing anchor, and please calculate the millisecond distance between these two waveforms. So that being said, when I look at my BSA application, I am going to toggle things over from my ECG channel to my finger PLE channel. And when I do so, you'll find that there is one other metric that is introduced here, which is pulse transit time. So unlike the HRV analysis app, where we are really concerned about continuity here, with PPG and pulse transit time and overlaying these signals, we are throwing continuity out the window. We no longer care if we have 30 seconds of continuous data. Instead, again, this is the overlay of these two waveforms. So we care about good R peaks and good systolic peaks on a cycle by cycle basis. So that being said, what the program is doing for you here is identifying the R peaks and identifying the peaks and troughs of this PPG signal. And from here, for each cycle that has a dot included on it means that it will be used in this PTT calculation, where in seconds, we can see that this is about 2.91 seconds after the ECG interval. So that being said, when we're going through and editing here, this is going to take a very similar approach to our impedance editing, if you're familiar with that, where we're going to go for the most impactful edits first, meaning taking out the big sections of movement that is going to inappropriately extend or shorten our PTT waveform. So as we look at these big sections of data or these big sections of movement, we're going to see differences in PTT between the segments as we let these influence the spacing of the intervals. So when coming through and trying to score for PPG data and PTT, again, we are going to go for the edits that are most impactful. So in this finger PLE data, when the signal starts to drop off, we can see here that we have continuous data. And let me actually. Okay. So we can see here that we have continuous data, but given the amount of movement and things being inappropriately flagged, we are extending these PTT times. So when we go into our signal editor here, again, we care about things on a cycle by cycle basis, but we're going to first start by deleting edits that would be most impactful, which is this dropout in signal in order to improve this PTT time. So just as a very global edit, I am going to come in and delete the 2 points between my X cursors and remove all of these cycles for being included in my PTT analyses. So that being said, as I scroll down and push this analysis window outwards, I was previously at a PTT of 2.421, but when I close and remove the section of data, we can see a drastic difference as far as this PTT shortening up relative to the actual cycle by cycle differences and or relative to the cycle by cycle differences, but really removing the data that was most affecting or extending this PTT time. So again, similar to impedance, you'll go for the edits that are most impactful first to improve your PTT interval. But again, we will also look at this on a cycle by cycle basis, meaning that in good sections of data, we will come in and zoom into our, there we go, after I zoom in on my Y a bit more, we will come in and determine from this waveform if we like the ECG peak, it's a typical waveform, PT-QRS, and we like the systolic peak, that we would include this in final analysis. However, with this finger PLE that we were looking at before, as we start to get down to it, given the lower temporal resolution, we're starting to see that we don't have as much definition around these individual peaks. So this is where we would essentially come in and, outside of those larger pieces of movement, make some deletions and insertions around beats that would not give us accuracy in timing. So same thing here, like impedance, continuity does not matter. So if we are deleting points, that is completely okay, because the remaining, they will not be included in our final PTT analysis, but rather only the cycles that have included dots will be. So after kind of going over this high-level overview of PTT, I'm going to transition us back into our slides. And talk a little bit about some of the data organization on the back end that I didn't go over today, but if you're familiar with our programs, you are used to this type of data organization and file structure. So when we're working with multiple waveforms, it's important that we get our analysis pipeline correct. So oftentimes, this will first start by scoring our HRV data alone if we are working with HRV and PPG at the same time. And this is so that we can score all of our HRV data and use those edits to leverage them within the BSA application in order to really rule out cycles that we know we don't want to use and just evaluate that PTT and PPG data. So we will similarly start an HRV and pass this pipeline down into BSA for PTT editing with PPG. Or if we are only editing PPG data, we would just begin in the HRV analysis application and go about saving our edit and output files within the same typical structure that we're used to. The most important thing here is that HRV and PPG do follow the same editing rules, but again, HRV is going to be more strict, more stringent, more published on rules. So for however you are setting up your data, let HRV be your roadmap for your segmentation across all other measures. So that being said, I would love to pop into the Q&A portion of today. I saw that a couple of questions came in during the webinar itself. So I'm just going to read off some of the questions that came in and then go ahead and work through each of these individual questions as a group. So I saw that someone mentioned that third-party devices may have PPG data limitations based on the device specs. Can you show a data example to visualize these differences? Yes, absolutely. Give me 1 second. I'm going to pull out of the presentation to pull up our HRV program once again. But this is a really great question because when we've talked about the specs of the device, the sampling rates of the device, we've talked about how this can be limiting in what data visibility you have. So I'm going to pull up in the HRV analysis app a file that only contains IBIs. So sometimes with PPT data, we may not get the full waveform, we may not get the waveform at all, but rather just the timing differences between these pulse-to-pulse intervals, which are used to calculate and estimate heart rate. So rather than this being the classic MWI file that we are familiar with in the MindWare ecosystem, this is instead going to be an IBI file where we have to define some areas of interest of what data we are actually looking at. So this will be different from device to device depending on what measures are being calculated and how the data is stored. But in my current file, I'm essentially looking at the millisecond difference between some of these different data points for timing, sampling, and IBIs. So when I go into the HRV analysis application this time, you'll find that this looks so different than what you are used to. Rather than seeing any waveform here, all that we are seeing is kind of these lines that are representing the IBIs or the pulse-to-pulse intervals of these beats. So that being said, as we start to consider using third-party devices, we need to really do our due diligence in making sure that we know what kind of data we'll be getting on our back end. Because with this, we have incredibly limited information. We can see that there's gaps in the data, but we don't know if this is due to movement, if this was due to sensor connection. It's not clear currently when we lack this waveform. So instead, when considering third-party devices, if you only need an estimation of heart rate, that may be fine for your purposes, especially if you're doing more ecological assessments outside of the lab. But generally, if this was something like we had purchased this device with intention to do pulse transit time analyses with ECG, no way, not happening at all. We don't have any precision around the systolic peaks. And so in order to get that millisecond timing difference to assess arterial stiffness, we simply just aren't using a device that supports the type of question we're asking. So that being said, something to consider here when thinking about your devices and making sure what data access you have, but then also considering those proprietary algorithms and raw data access. Great question. I'm going to pull up our presentation again and give me just 1 second as I peek at our next question. Okay, so another question that came in was, what type of PPG signal is generated using MindWare, and what are the advantages of each? So we have When looking at the signals that are generated of MindWare, we have a reflectance for the finger strap. And this is nice because for its advantages, the sensor, when reflectance, can be placed almost anywhere on the body. Ours is outfitted to be on a finger or on a toe as well. And reflectance does not require a clip on the tissue. So instead, with transmission for the ear clip, we're able to see higher signal quality and less sensitive to movement artifacts. So again, this is reflectance versus transmission. And so depending on the sensor that you choose, will also have a downstream effect on your waveform visibility. The next question that came in was, does finger versus ear placement matter? And kind of alluding to what we just talked about as far as the type of PPG signal that is generated, we also need to consider the placement site. So site choice definitely makes a difference. And site choice can affect participant comfort, motion sensitivity, and waveform stability. So in some cases, one site may produce a cleaner or more stable signal depending on the participant and the task. So for example, if you were someone who was working with a parent-child dyad doing a play task, you may be more likely to opt for an ear placement if you are having the kids and parents down on the ground using their hands and playing with toys. This will just reduce any movement that you see within the signal. And again, going back to the reflectance and transmission, depending on the site that you choose, will also determine the visibility of your waveform. So a few things to consider here. Who are your participants? What are your tasks? And how precise of a waveform do you need? The next question that came in is asking, what should I check first if the PPG waveform in my preview screen does not look right? This is a great question. So when going back into data acquisition, when we're in BioLab and hitting our preview screen, we're able to look at our waveform before we actually begin recording in order to make any changes as needed for improving our signal quality before actually beginning the experiment. And with that, the very first things that I would start with are definitely going to be sensor placement and contact pressure. So if we're lacking definition around some of our systolic peaks, it may be that we need just a more snug fit on the PLE. And we'll also want to reduce participant movement and make sure that just the PLE cable isn't getting tugged on or is out of the way for the participant during the course of the experiment. Okay. Okay. So the next question that we saw come in. So this is going to be actually our final question of the day as well, too. So can poor PPG signal quality affect pulse transit time? Absolutely. I think that this totally relates to the first question that we were talking about, depending on a multitude of things, depending on the quality of your device and the visibility that you're able to get. For example, in that IBI data, we don't have any waveform whatsoever to talk to millisecond differences of PTT between R peaks and systolic peaks. So it depends on your device and your waveform, but then it also depends on the signal quality itself. So as we talked about with that finger PLE, we saw that there was less precision around the systolic peak. And therefore, if it was something that we saw kind of as a common theme across the segment epic or entire participant file, that would determine the overall usability of PTT. But again, we care less about continuity with PTT, that we're able to kind of pick the cycles to inform these millisecond differences, even if we have large sections of movement riddled within it. Okay. So, just as a reminder, for resources, now that we are wrapping up the webinar today, I first wanted to remind you guys of some resources on our support site and also some new resources that will be coming out. So for our support site, you will find our training guides listed on there. And these are really great starting points to essentially learn more about an individual measure and really get a breakdown across various resources and articles of what the measure is, how it's used, what the waveform is like, and how to clean and analyze it. So we have these training guides built up for HRV, ECG, and EDA. And when we send you guys the recording of this webinar, we will also be releasing a PPG training guide as well. So that being said, pay attention to that. In addition to this webinar, you'll find additional readings, resources, and citations that inform some of these decisions. And while talking about our support site with our training guides, I also wanted to highlight some of the other sections of our support site that can be of most use to you. So number one, you can get in contact with us through our support site and open a support case or consider scheduling one-on-one training if you would like to chat with me in more detail about your data specifically. And additionally, from here, outside of getting in contact with us, it also nests the downloads and all of our knowledge base articles, which are a great resource to start with whenever you have questions about the equipment that you're using, or you have questions about configuring your Bionex for PPG. All things from technical wherewithal of how to work our hardware and our software in the MindWare ecosystem to more about the measures and integrations you can work with as well too. So in addition to that, I also wanted to bring your attention to our main page as well. So our support site will have all of this amazing information as resources, but our main page will also nest things like our web store where you can purchase electrodes or any disposable equipment that you need. And most importantly, if you have a very complicated question, you want to get in contact with us directly as far as troubleshooting or inquiring about different products like the BSA application or PLE, please feel free to either call us or email us at support@MindWare Tech or sales@MindWare Tech. And lastly, you've sat through this webinar today and you may go, okay, great. I learned a whole lot about how to score my PPG data and how to score pulse transit time. But you may also be sitting on a whole backlog of archival data that you still need to score. And if you went, I still don't know if I have enough time to do all of this, we can actually score your data for you. So not only do we provide the hardware and software of the systems you use to record this data, but if you have a big backlog of data that you want to try to make headway on and be a transitioning graduate students or scorers and editors, contact us at our sales team. We can score any type of data that we currently collect within our MindWare ecosystem. And we will consult you all along the way to make sure that we are pulling the correct segmentations, metrics of interest, and analyses that you would want, all exactly as you had planned, with just out any of the work. So if that's something you're interested in, let us know. And Since we talked about the in our 25th year anniversary, we will be coming out with new lines of technology for both hardware and software. I would also encourage you to sign up for our newsletter on our support site. This will keep you up to date with all of our new announcements, when our next webinars are going to be, what these new lines of tech are, outside of me just teasing them. So to be the first to know, go on to our support site and subscribe to our mailing list, and then you will be in contact about all of these new and exciting news in the pipeline. So most importantly, thank you all so much for attending today. Again, this is a very important year for MindWare that we're excited to have you as we continue our education initiatives with our webinars. And if you would like to join us for our next webinar, we will be presenting another complimentary webinar on July 16th, 2026 at the same time. So this webinar will really build off of the concepts that we talked about today, where we were talking about pulse transit time. Next time, we're going to be talking about pulse wave velocity, where we take this pulse transit time and consider the distance of which it's traveled, often when using dual impedance, in order to get an even better look at arterial stiffness and really speaking to the time it travels of that pulsate waveform. So if you are interested in joining us, we also have a QR code here that you can scan and sign up for at this time. So thank you guys so much. That will conclude our webinar for today.